the security mindset. Let me start with the simplest possible way to see this. Imagine two people looking at the exact same door. A builder looks at the door and asks, "Does it open and close properly? Does the key work?" "Yes." "Good. Done." A security person looks at the exact same door and asks a second, different question. "Could someone get through this without a key at all? Could they pick it, kick it, or walk in through a window I forgot was unlocked?" Same door, two completely different jobs. That's the entire mindset shift in one image. How it actually works in depth. Let's translate that into real code, because this is what you'll actually be doing. Imagine a simple function called getOrder. It takes an order ID and returns that order from the database. As a developer, you test it, pass in order ID 5001, you get order 5001 back. Correct. Ship it. Now look at the exact same function with the second mindset. Ask, what if I don't pass in my order ID? What if I pass in someone else's? Looking at the code, there's nothing here that checks who's asking. The function will return any order to anyone, as long as they know or can guess the ID. Notice something important. The code isn't broken in the traditional sense. It does exactly what it was written to do. There's no typo, no crash, no error message. The gap is entirely in what the code was never asked to check. That's the core skill of this whole field, learning to see the question that wasn't asked, not just the bugs that throw errors. Its role in the appsec field ****. This mindset isn't one topic among many in security. It's the operating system underneath every other topic you'll learn. When you study injection, broken authentication, broken access control, every single one of those is really just the same mindset, applied to a different part of an application. In an actual appsec job, this mindset is what you're being paid for, more than any specific tool. Scanners and automated tools can find a lot of known patterns automatically. What they can't do well is look at a feature that's unique to your company's business logic. A custom discount code system, a specific checkout flow, a particular way orders get assigned to warehouses, and ask, how would I personally break this if I wanted to? That creative, adversarial thinking is specifically the part of the job that stays human, even as tools get better. Why it matters. Here's the honest stakes. Every vulnerability you'll learn about this week, injection, broken authentication, broken access control, misconfiguration, exists because somewhere, a developer asked only the first question, does this work? And never asked the second one. They're not different skills. They're the same missing habit showing up in different parts of the code base. If you only take one thing from this entire course, take this. Before you ship anything, get in the habit of pausing and asking, if I were trying to abuse this instead of use it normally, what would I try first? That single habit, practiced consistently, prevents more real-world security incidents than almost any specific tool or certification. Injection. Imagine a login box on a website. You type your email and your password, you hit submit. Normally, the website checks, does this email exist? Does this password match? If yes, you're in. Now imagine that instead of typing a real email, someone types something strange. A little snippet that looks like computer code instead of an email address. If the website isn't careful, it can accidentally treat that strange text as an instruction instead of just a piece of data, and end up doing something the developer never intended at all. That's injection in one sentence, user input that gets mistaken for a command. How it actually works. Let's go under the hood. Behind that login box, the server typically builds a database instruction that looks something like, find me the user where email equals, and then it pastes in whatever you typed, and password equals, and pastes in whatever you typed there too. If you type a real email and password, this works exactly as intended. But what if, instead of a real email, someone types this, ''1'=1'1, to a human that looks like nonsense. But remember, this text gets pasted directly into the database instruction, exactly as written. Once inserted, the full instruction effectively becomes, find the user where email equals nothing, or 1 equals 1. And here's the critical detail, 1 equals 1 is always true, for every single row in that table, no exceptions. So the database essentially says, well, this condition is true for literally everyone, and logs the attacker in, often as the very first account in the system, which tends to be an administrator. Nobody guessed a password. Nobody stole a file. The attacker simply talked the database into agreeing with a statement that's always true, because their input was treated as part of the instruction, not as data to be checked against. Its role in the appsec field injection is historically one of the most damaging vulnerability categories in the entire history of software, and it's the reason an entire category of tooling exists, things like SAST, static analysis tools that scan your source code specifically looking for places where user input flows into a query or command without being properly handled. If you end up working with devsecops pipelines, one of your very first jobs will likely be configuring exactly this kind of scanner and learning to tell a real injection risk apart from a false alarm. It also tends to be one of the first things any technical interviewer will ask you to explain and demonstrate because it's foundational. If you can't reason clearly about injection, it signals you may not yet have the core mental model down for everything else. Why it matters: the real-world consequences of injection are some of the most severe in the field, because a successful injection attack frequently doesn't just expose one user's data. It can expose the entire database at once. Some of the largest publicly known data breaches in history trace back to exactly this category of flaw. And the fix is genuinely not complicated once you know it. Never paste user input directly into a query or command. Always keep user input strictly separated as data. The damage to difficulty ratio here is part of why this stays critical to no code. It's a relatively simple thing to prevent, but catastrophic when missed. Broken authentication. Think about how you prove your identity at, say, a bank. You show ID, maybe answer a security question, maybe get a code sent to your phone. Authentication online works the same way conceptually. A password, sometimes a second code, proving yes, this really is me. Broken authentication is simply what happens when that proving process has a weak point, something that lets a computer or an attacker convincingly pretend to be someone they're not. How it actually works. Let's go through 3 specific, very common ways this breaks because each one teaches a different lesson. First, no limit on login attempts. If a login page never says, "You've tried too many times," slow down. An attacker can write a small script that tries 10,000 different passwords against one account in a single minute. With weak or reused passwords, which are extremely common, one of those guesses often works, purely through brute force, not cleverness. Second, session tokens that never expire. When you log in, the system usually hands your browser a token, digital proof that says, "This browser already proved who it is. No need to ask again." If that token is ever stolen through public Wi-Fi, a malicious extension, a poorly secured device, and it never expires, the thief now has permanent, undetectable access, indistinguishable from the real account owner for as long as they choose. Third, and genuinely alarming when you first see it, a password reset feature that emails you back your old password. Pause on why this matters. For a system to email you your original password, it must have stored that password somewhere it could read again later. That means the password was never properly hashed, never run through a one-way mathematical transformation that makes it permanently unreadable, even to the company itself. If that database is ever breached, every password in it is exposed in plain, immediately usable form. Its role in the appsec field. Authentication sits at the very front door of almost every system you'll ever assess. Because of that, it's one of the first things any security review checks, and it's an entire specialty area on its own. Concepts like multi-factor authentication, single sign-on, and token management are deep enough to be full-time roles by themselves at larger companies. If you move toward API security specifically, given your background, you'll deal with authentication constantly because almost every API integration question eventually becomes, how does this API know who's calling it, and how do we know that proof can't be faked or replayed? Why it matters. Broken authentication is uniquely dangerous because it doesn't just expose one piece of data, it hands over an entire identity. Once someone can convincingly pretend to be a real user or administrator, every other security control built on top of "we know who you are" collapses because that foundational assumption is no longer true. This is why rate limiting, token expiration, and proper password hashing aren't optional best practices. They're the floor that everything else stands on. Broken access control. Imagine checking into a hotel. The front desk correctly checks your ID, confirms your reservation, and hands you a real, valid keycard. No problem with any of that. Now imagine that keycard actually opens every single room in the hotel, not just yours. The front desk did its job perfectly. They really did confirm who you are. The failure is entirely in what that keycard was actually programmed to open. That, in one image, is broken access control. How it actually works in depth. Let's make this concrete with an example close to backend and API work. You're logged in as customer number 50. You go view your own order history, and your browser sends a request. Get/API/orders/5001. The server responds with your order correctly because order 5001 really does belong to you. Now here's where it breaks. What happens if you simply change one number in that same web address, from 5001 to 5002, and send the exact same kind of request? In a properly secured system, the server should respond, "That order doesn't belong to customer 50. Request denied." But in a system with broken access control, the server instead responds with success and hands over order 5002 in full. Someone else's name, someone else's address, someone else's order contents. Walk through the server's actual logic to see exactly why. The server checked one thing. Is this a valid, logged-in session? Yes. Approved. It never asked the second, equally necessary question. Does this specific order, the one being requested right now, actually belong to this specific logged-in person? That check simply doesn't exist anywhere in the code. The login system works flawlessly. The ownership system was never built. This category also goes by two other names you'll hear constantly. IDOR, Insecure Direct Object Reference, and BOLA, Broken Object Level Authorization. Different names, same exact root cause. Its role in the appsec field. This is currently ranked the number 1 risk on the entire OWASP top 10 list, and for good reason. It's extremely common, and it's almost invisible during normal development testing. If you test your own order page using your own account, everything looks completely correct every single time because you're naturally only ever testing with IDs that belong to you. The bug only reveals itself when someone deliberately tries an ID that isn't theirs, which is precisely the kind of adversarial test that standard QA processes routinely skip, because QA is built to test, does this work? Not, can this be abused? Given your specific background in API integrations, this is genuinely the single most relevant category for you to master deeply. Almost every API endpoint that returns or modifies a specific record, an order, an account, an invoice, a shipment, is a candidate for exactly this flaw, and reviewing endpoints for proper ownership checks is core, everyday work in API security roles. Why it matters. The damage here tends to scale linearly and predictably. If customer order IDs are simple sequential numbers, an attacker doesn't need to find one flaw. They can write a short loop that walks through every single ID in the system, silently harvesting every customer's order history, one request at a time. This has caused real, large-scale data exposures at real companies, often discovered only after months of quiet, ongoing access. The fix is conceptually simple: always check ownership, not just login status, but it has to be deliberately built into every single endpoint that touches user-specific data. There's no single global setting that fixes it everywhere at once. Security misconfiguration. Imagine moving into a brand new house. The house itself is well built. Solid walls, good wiring, everything structurally sound. But you never bother changing the locks the construction crew used while building it. The house is fine. The forgotten setting is the actual risk. Security misconfiguration is exactly this, applied to software. The danger isn't in how something was built, it's in a setting that was simply never changed from its out-of-the-box default before going live. How it actually works in depth. Let's go through 3 real, common examples, each teaching something slightly different. First, debug mode left on in production. Debug mode is genuinely useful while building something. When an error happens, it shows the exact file, the exact line number, sometimes internal configuration values, which helps developers fix problems quickly during testing. The problem is when that same detailed error page is shown to the public after the system goes live. Now anyone who triggers an error, sometimes completely by accident, can see internal file structure, system details, and in some surprisingly common real cases, even database connection information. Second, default admin credentials left unchanged. Many systems ship with a built-in starter account. Something like username admin, password admin, specifically meant to be changed immediately during setup. Under launch day deadline pressure, this is one of the easiest steps to simply forget. Attackers know this extremely well. Trying admin/admin against newly launched systems is one of the most basic, most automated attacks that exists, precisely because it keeps working often enough to be worth trying everywhere, constantly. Third, increasingly relevant with cloud infrastructure. A cloud storage bucket accidentally set to public instead of private. Many e-commerce platforms store files, customer documents, exported reports, sometimes backups. In cloud storage that defaults to private but can be flipped to public with a single misclick or a copied configuration. Once that happens, anyone who knows or guesses the right URL can read every file inside, with no login required at all. Its role in the appsec field, what makes this category distinct from the others, is that it lives entirely outside the application's actual code logic. The checkout function, the order processing function, might be flawlessly written from a pure coding standpoint, and the system can still be wide open because the vulnerability sits in the configuration and infrastructure layer surrounding the code, not in the code itself. This is exactly why devsecops exists as a discipline, and why security increasingly gets built directly into deployment pipelines rather than checked only at the end. A well-run CI/CD pipeline, the same kind of Jenkins or GitHub Actions pipeline you've likely already worked with, can be configured to automatically verify these settings before every single deployment, catching a forgotten default before it ever reaches production, rather than relying on a human to remember a checklist under deadline pressure. Why it matters. These misconfigurations are often the easiest vulnerabilities for an attacker to find, precisely because they don't require discovering some clever flaw in custom code. They only require checking a small, well-known list of common defaults that many companies forget to change. That low difficulty, combined with potentially severe consequences, full database exposure, complete administrative access, or an entirely open file store, is exactly why this category consistently appears near the top of real-world incident reports, year after year, despite having no genuinely difficult technical fix at all. The fix is overwhelmingly about process and discipline, not advanced technical skill, which honestly makes it one of the more achievable areas to get very good at quickly.